Hi, Ben Constable with you from Sparx Systems. This presentation is for our software engineers, analysts and architects who are charged with documenting and maintaining existing or legacy systems. At some point, you're likely to inherit a large code base, perhaps poorly documented, and it's your job to understand how the application works, to make bug fixes and enhancements, or even to migrate the system to a new platform. Now, even with a modest-sized application, manually trawling through the source code, line by line, file by file, is a tedious exercise and doesn't help you get the big picture quickly. So what tools does Enterprise Architect offer to help you solve this challenge? And how can you use Enterprise Architect to discover not only the system's static structure, but to understand and document its runtime characteristics as well? Using a sample legacy application that simulates a passenger train network, I'll explore 3 key ways in which Enterprise Architect can fast-track your analysis and visualization of existing application codebases. First, I'll show you how to automatically model the application's static structure by reverse engineering the application code into a UML class model. Next, you'll see how to get a quick overview of the application's runtime behavior by profiling the application as it executes. Finally, I'll show you how to automatically generate visual aids in the form of UML sequence diagrams as you record the running application. This facilitates your own understanding of the legacy system and produces documentation deliverables for you. To give you some context on the example, here's the legacy application running now. It simulates a metropolitan train network. The moving dots represent trains travelling between stations as the application tracks passengers embarking and disembarking at each station. We wrote this sample application in C++ using MFC, but EA can reverse engineer most of the languages you're likely to encounter in your own projects. So you can just follow the same basic steps I take throughout this presentation. You start reverse engineering the application by importing your legacy code into an Enterprise Architect model, assuming you have the code available. By doing this, you'll get an overview of the code's static structure, so what classes are involved, their relationships to other classes, and their properties and methods. You'll also be able to trace back to the code later when you start visualizing your application's runtime behavior. With a model open in Enterprise Architect, let's import some code. Invoke the code importer from the project browser by right-clicking the package under which the code model will reside. Choose Code Engineering, Import Source Directory. The root directory is where you want EA to start looking for your code. From the source type drop list, choose the original programming language. Then you have various options to modify how the import works, such as whether you want EA to search subfolders for source code files as well. Or you might want to suppress details in the auto-generated diagrams to get more of an overview. For example, I'll hide the class properties at first, so I can focus on the relationships between classes. Say OK, and EA will import your application code for you. So what does our reverse engineered code reveal? Looking at the project browser, we see the application's 10 custom classes and the type definitions. Drilling down, the class members are represented as UML attributes and operations. And we can readily trace now between model and code. Just right-click and choose View Source Code to jump to the definition in code. The UML diagrams provide a reasonable overview of the relationships between the classes. Being auto-generated, you might clean them up using EA's various layout tools. And here's an example where I've chained a couple of layout algorithms together, and that gives a reasonable job, but I'm still inclined to make some manual tweaks, especially if I'm going to share the generated documentation from these diagrams. As they say, here's one I prepared earlier. So it's readily apparent that the train and station classes share a parent in T-object. C-train also makes use of the network class and holds 2 references to C-station, presumably specifying where it's arriving or departing from. Now if you want to show the full class details on diagrams, that's easy. Just right-click to open the diagram properties and show the compartments you need, or you could even specify which type of class members you want displayed. Better still, create more focused diagrams where you show the properties and relationships for particular classes of interest, just as I've done in this diagram here. So far, we've gained insight into the structure of our legacy application by reverse engineering the static code into a UML model. But what does the application actually do when it runs? Where does it begin? What classes and functions are involved? Where is most of the time spent? And how would we document what it does? Well, these questions are what EA's Visual Execution Analyzer is designed to answer. The Visual Execution Analyzer, or VEA, consists of a suite of tools that help you explore your system's runtime characteristics. When investigating a legacy system, one of the first tools you might consider using, even before inspecting the code, is the profiler. It extracts valuable information about a running system by recording samples from its call stack over a period of time. This quickly gives you an idea of an application's most commonly called methods. The two primary use cases for the profiler are, firstly, to get information on where a running system spends most of its time, so what functions are called, how often, and how long do they take to execute. This is useful, for example, if you are performance tuning an application. Secondly, as in our case, the profiler helps you understand and document the system's runtime behavior. We can answer questions like, where does the system even start? When I push a given button, what parts of the application codebase am I activating? Our goal is to have the profiler automatically generate reports for us that answer questions like these. You invoke the profiler from EA's Analyzer menu. The profiler functions are all available from the toolbar in this dockable window, so you can start and stop the data collection, auto-generate reports, and adjust the sample interval here. Before the profiler can start sampling call stacks though, you need to point it to the application you're interested in. You can do this simply by attaching to an already running process. Otherwise, you configure the profiler using an analyzer script in EA, which specifies things like how and where your application compiles and runs. Let's create an analyzer script now. And no, this doesn't involve any programming. Each analyzer script is bound to a package in EA's project browser. You manage your analyzer scripts from the Execution Analyzer window here. Click to create a new script. Select the package that contains your implementation model. Now first I'll specify how EA should build or rebuild the application. I want to execute the build as a process using this build command. The identifier between the % characters here is just a shortcut to the full folder path on my local machine. I created this shortcut using EA's local paths feature, which is handy if I share the model with other users, as the path to the code on their machines may be different. It also helps in case I change the location of the code on my machine in future. The default directory here tells EA in which directory the build process should run. Again, I use the local path symbol to help me there. Now I can do likewise to specify the build clean command. Finally, I need to specify the application's debug parameters. First, the debugger to use. Well, being an old MFC C++ application, I choose Microsoft Native. Then I specify the relevant paths for the debug process and the compiled application itself. Click OK, and our completed configuration is now listed here among EA's Analyzer scripts. Right-clicking the script, I now have access to any commands that I configured via the script. For example, I can rebuild my legacy application easily from EA now. I want to do this just to make sure that my application's debug binary matches the codebase I reverse engineered before. As you can see in the system output, that build was successful. Now let's have the profiler collect some data as we run the application. I'll choose to start data collection immediately as I want to see everything from the application startup onward. Clicking the play button will invoke the debug build of my legacy application as specified in the analyzer script, and the profiler will start recording samples from my application's call stack. So here's the train application running as a separate process, and the profiler has begun recording. Notice the entry point here, which appears to relate to the application's startup routines. Now when I click the application's Run button, the train network simulation starts. Notice the second entry point that appeared when I clicked Run? This will show me what methods are invoked when I use this feature of the application. Now I stop the profiling by closing my application. There's a brief summary in the profiler window, but we can get more detailed reports by clicking on this icon. We can see immediately that most of the application's work is done in this startup entry point, and as we drill down, most of these items relate to system calls for painting the application window. From a percentage basis, 74% of the samples relate to this entry point, whereas only 26% of the work is done in the application's train simulation code. That alone tells you there's not some disastrous bottleneck here in the actual simulation code itself. Drilling into that entry point, we can see easily what code executes when the application's Run button is clicked. The ctrain class is involved, and specifically a call into its Run function. I mentioned before about being able to trace back to the code. Well, that's as simple as right-clicking and viewing the definition. Now the call stack for our rail simulation is not that deeply nested or particularly interesting because it really is a fairly simple application. But our own engineers have benefited from using the profiler on much larger applications, not only Enterprise Architect itself, but third-party libraries as well. You'll see an example of that in the profiler topic of our user guide. One of our developers really benefited from profiling the Xerxes XML parser before having to use that library himself. From a documentation point of view, we have a real advantage now because we can model these weighted call graphs visually using UML. As one example, I'll generate a sequence diagram that represents this particular branch of the call stack. So this format can be a little easier to digest. As you investigate in more detail, you can even generate function line reports for specific calls. Take the run method, for example. How do you know what parts of that function are executed for a given use case? Well, the profiler can tell you that. Watch as I run the report, which will also start up my application. Now I click the Run button because that's our use case. Now you can see in real time exactly what parts of the function are executed and how often. We've used this capability ourselves here at Sparx Systems, and it's proved valuable in helping to identify existing application code that needed to change. While the profiler can give you a good sense of the main methods involved in your application, it won't give you a precise sequence of calls that are invoked for a given use case scenario. And in the early stages, you don't really want that anyway. Remember, the weighted call graph produced by the profiler is based on sampling the call stack at short intervals. It doesn't just regurgitate the call stack for you line by line. But when you do want more detail, say to document the exact sequence of calls made by your application for a given use case scenario, the Execution Analyzer's recording tool gives you that detail, and it produces the UML model documentation for you. The recorder uses special breakpoints or recording markers set against the application's source code. From our profiling results, we saw the simulation begins from the train class's execute method onwards. So we locate that method in code. From the project browser, go to the ctrain class to view its code, find the execute method, we open up its definition, because we only record against these real lines of code. Notice in the margin, I can right-click to add breakpoints, which pause the program's execution so you can step through line by line, or to begin and end recording a section without interrupting the program, and that's more like what we need. And this handy marker lets you auto-record a given function by combining a start and a stop recording marker into one. That's what I'm going to use. Now, EA helps you manage all your breakpoints and markers in one place. Open the Breakpoints and Markers window from the Analyzer menu, and you can save various markers into your own named sets according to your analysis context. Okay, so let's record the execute function using this breakpoint set, city train run. You access the recorder from the Analyzer menu. Like the profiler, it can attach to and record from a running process and produce model documentation based on its results. Here you control the stack depth to record to. Click play to start the application and the recorder, and you're prompted for options such as the marker set to use, and you can see how your running application compares to any state machines you might have defined against the application. Based on my current understanding of how the train should progress from station to station, I did define a state machine in this model that matches the original spec. So I select that and then record. You'll see that the application's pretty slow now because we're recording almost all the application, which is going to tax your system somewhat. But let's stop and see the results already. You see each method call is listed in detail, and each train thread denoted here as a separate instance. Really, it's easier to share this information in diagram form, so let's generate the sequence diagram. So here are the 3 train threads you saw moving on screen. You can see the calls they make to other classes. And EA has overlaid the state information on each instance. So this is their starting point. But you can also see the app is calling these get speed and get location methods a lot. So there's a bit of noise coming from those getters. I'll show you how to filter that out now. From your Analyzer script, head to the Recording tab and make sure Enable Filtering is selected. In the exclusion filters, you see I already excluded from my recording any of the really low-level repetitive methods. But you can specify any others by writing first the class name, followed by the method name, and you can even use wildcards for a more general filter. Okay, let's rerun the recorder. Again, I select my state diagram for a comparison. Let's speed up the simulation a little. Now, stopping the simulation, let's regenerate the diagram and see. Okay, that's certainly clearer. And scrolling down, you see some invalid state transitions highlighted. See how the train tries to go from Lonsdale to Spencer, then Spencer to Central? Let's open up the original state diagram and compare. Well, that train was in trouble. From my own experience, I know this ordering of stations is correct. So my simulation first sent the train backwards to Spencer Street, then tried to send it through a brick wall here to go directly to Central Station. Time to investigate the code and find out why. We'll start with the application's initialization code. Notice the function onInit dialog. Let's open its definition. And here we find the problem. Spencer Street should come before Lonsdale. So correct that order, and that should fix our issue. So Our original sequence diagram with state information overlaid helped us to really troubleshoot the legacy app. So today I've shown you some of EA's powerful software engineering and visual analysis tools. I used a legacy C++ application as an example, but you can apply the same approach to other technologies as well. To recap briefly, importing your codebase into EA provides a quick way to visualize the static structure of your application. This reverse engineering process also facilitates traceability between an abstract design view and your source code. You can start exploring the runtime behavior of your application using EA's profiler. Not only will this assist your own understanding, but you can auto-generate useful documentation too and visualize the call graphs using standard UML notation. The recorder helps you trace the running application in greater detail. By using recording markers against the original source code, EA will automatically generate sequence diagrams, showing you how the application responds to a given use case scenario. Well, that's it for now. Until next time, happy modeling.